Hello everyone, my name is Nehal Desai and I will be going over pharmacy calculations with you all. This is a lengthy presentation, so I will go as quickly as I can to get through most of the concepts here. Um, Feel free to pause the video in between if you'd like to take a moment to um, practice any of the questions that's in these slides here. And let us know if you have any other questions. So um, this is a slide that talks about what is covered in pharmacy calculations overall. You're going to start with the basics, which is basically learning how to convert between one unit to another, milligrams to grams, fluid ounces to fluid grams, or vice versa. And you're also going to see how those conversions occurred. And as you're doing these practice problems, you'll be able to be familiar in doing these so that you can apply them in the more um, clinical scenarios in terms of like applying it throughout pharmacy calculations. The next thing we're going to be going over are some compounding clinical calculations that actually apply concepts of unit conversions. And each of these um, concepts utilize the previous concept. So you have to know things from the previous concepts to be able to apply it in the later concepts as they show up. There are a few exceptions, obviously, like DEA numbers. You're not going to probably need to know any unit conversions and all for that. But I will show you how that works as well, what that is. Um, you'll see a lot of um, calculation questions regarding dilutions, reconstitutions. You're going to see some of those on percentages and ratio strengths, alligation techniques, alligation alternate or mixed. When two uh, drugs are mixed together, you'll see how to do those types of calculations. Isotonicity to figure out, the um, how to make the drug similar to the osmotic pressure and all. So you'll see all that as well. And the pH and pKa, Henderson-Hasselbalch equation when it comes to the buffers um, section of this pharmacy calculations course. We'll also be going over some IV infusions, TPN related, which involves the total parenteral nutrition, which is in the third bullet point on the right. Pediatric dosing, there might be some questions on that. I probably didn't include that many questions on it because this mainly like making those kinds of conversions and all. And I'm sure some of you have seen like dimensional analysis in your chemistry classes. It's very similar to these kinds of concepts. So you're probably not going to need to know a lot more of that. However, if you'd like more practice questions, I can provide them to you. Um, there will be some questions on in pharmacy calculations related to electrolytes, which involves milliequivalents, millimoles, osmolarity. So it's important to understand those differences, how they're used in pharmacy calculations, and being able to solve them. The other part are some clinical calculations. You're going to need to know how to calculate creatinine clearance, the ideal body weight, the surface area and the body mass index, and applying Harris-Benedict equations as well. We'll talk about the stress factor and activity factor that's in as used in this equation as well. DEA numbers, this is the part where when you're in a pharmacy and you have to validate a prescriber's DEA, when a patient drops off a prescription, you're going to need to check to see if that controlled substance is valid based off the DEA license number printed on there, or written on there. I will show you the steps on how to figure out the validity of a DEA license number in this calculation course as well. There are a few insulin problems that you may encounter: reconstitution, capsule compounding. These are relatively pretty simple questions. I put in a little more reconstitution problems because some of you may get a little confused on that. So hopefully this presentation will clear up some confusion there. So the first thing we want to focus on here are really just understanding the calculation references. These include things like understanding the apothecary units of fluid. You have like the 60 minimums, 8 fluid drams, 16 fluid ounces, 2 pints, 4 quarts, all those liquid amounts, units that you should be familiar with, or at least have them memorized as you're taking your pharmacy calculations course in school, or when you're preparing for the NAPLEX pharmacy boards exam. This is another units of weights conversion that involves grains, ounces, pounds. Just be familiar with this as well, and also the SI unit equivalents. That basically involves things like length, where 1 inch is equal to 2.54 centimeters, the volumes, the weight, and at the end here, obviously, the English conversions, which involve the 1 foot equals 12 inches. I put 2 other things down here about teaspoon and tablespoon. It was not listed in these references when at the time of uploading it. So 1 teaspoon equals to 5 milliliters, and 1 tablespoon equals 15 milliliters. So be sure to remember that. You're going to see it quite a bit in your future exams. These are some common pharmacy abbreviations that you should be familiar with. In practice, you'll probably see some of these abbreviations on a prescription. You're probably going to see it. So be familiar with how these abbreviations are used, especially in this calculations course. So moving on, these are just some pharmacy conversion practice prompts that you all can use to practice with. These are just some random questions, and you guys can take the time to practice these. I have also posted the answers here, so you guys can use one slide to practice, another slide to see the solution. And that's how it's going to go throughout this presentation, mostly. So feel free to use this as a reference as you're practicing pharmacy calculation questions. Another quiz. This is quiz on the pharmacy abbreviations. There are quite a bit here that you can use to practice, and here are the answers to them, so you guys can take a look and see what they are. This is a question regarding compounding capsules. You can see here there's a prescription that consists of 3 ingredients. You got here the acetaminophen, which comes with an amount of 1 grain, caffeine, which has 2 grains, and then lactose and QS. So QS, you may see this quite a bit. I have seen it in practice. QS is, you could say, sufficient quantity or quantity sufficient. Um, this is the part where you're going to have to perform some calculations to figure out how much lactose is needed, or other sorts of calculations in these types of questions. Um, it looks like a prescription wants you to prepare 24 capsules, and the directions should state to take one capsule by mouth every 8 hours as needed for headache. So the first question here is to calculate the amount in milligrams of each ingredient required to prepare the prescription. This is where you're going to have to utilize the unit conversions to convert the grains to the amount of milligrams for each of these prescriptions. Then you're going to need to rewrite the prescription directions in a suitable language for a patient label. So you don't write things like 1 QD on a prescription label, or 1 BID, or 1 Q8H. You have to write the directions out so that the patient can understand how to use that particular medication or compounded medication. So take a moment and try to answer these questions. Okay. I'm going to move on. You guys can pause this video and try to work out the problem and answer this question. Here is how the um, calculation is performed, how it's actually solved. You'd look at each of these ingredients, and you would calculate the amount of milligrams. Now, you saw lactose as QS, and you wouldn't be able to figure that out unless there was an actual total amount of the compounded medication. So they have not provided that. So they have only provided you acetaminophen and caffeine. So those are the only two calculations that you'd be performing to answer this question. So the next one is another compounded medication. It's on Magic Mouthwash, and it involves three of these ingredients. Sometimes Magic Mouthwash, you might see four ingredients, um, and sometimes you see three. Um, Prescribers, when they call it into the pharmacy, they may call it in as three ingredients or four ingredients. Either way, you're going to have something like Maalox, lidocaine, and Benadryl in some form and in some way in the Magic Mouthwash. In this question, it says to prepare the following oil rinse, and this involves diphenhydramine elixir, 2 fluid ounces, lidocaine viscous, which is 1.5 fluid ounces, and aluminum hydroxide, magnesium hydroxide suspension, which is quantity sufficient. And let's look back and see what AD is. Some of you might not be familiar with AD. So AD is right ear. So these are things you should know by now, how to understand these abbreviations. So Magic Mouthwash, this seems a little bit off. AD is interesting. So I'll get back to you on this and another time, but maybe I'll repost this slide for you all so we can see what this question is talking about. So don't worry about this slide, just ignore this slide. I think something is off about this. So anyways, that was it for the compounding. Um, the magic mouthwash didn't really make sense, especially where they put AD. We will look more into it, and let you know once we have that edited version for you all, so we can um, give you the most accurate slide there. The next part is really the conversion questions, just converting between, different conversions and um, the quantities, looking at these different conversion. These are some more practice prompts for you all. And then here are the solutions to them. Apothecary to avoirdupois. This is another part of the calculation reference sheet you can use to practice in doing these kinds of conversions. I listed the answer here for you all so you guys can see that. The next part, we're skipping all the way down to the easier section, which is the DEA calculation reference. When you calculate DEA, or to figure out if that is actually a valid DEA, you will ignore the first two letters of the DEA license number, and you're just going to focus on the values that are next to it. So you can see here 5623740. The first step is you want to add up the first to third and fifth numbers, and then add the second, fourth, and sixth numbers twice. And you can see them color coded here for you in red and then green. You would add everything together, and then you would get 40. And what you would do with that value is the second digit should match the last digits of that DEA number. If it does not match, then that DEA number is invalid, and you may need to call the prescriber to figure out, what their DEA number should actually be, or, figure out what the valid DEA is. Or you may have to refuse the prescription altogether because of the DEA number being invalid for that controlled prescription, controlled substance prescription. So this is another practice problem on DEA number, and just to check to make sure what the DEA number should be. Here in this case, it looks like the DEA number was invalid, so you would write out the correct DEA number, and that would answer this question. The next thing is on percent strength. Now, percent strength involves the percent weight over weight, which could involve grams of solute per 100 grams of total product, or percent weight over volume, which is grams of solute per 100 milliliters of total solution. Percent volume over volume is the milliliters of solute per 100 milliliters of total solution. And those are important concepts to understand when it comes to percent strength. Here's a practice question. A cream contains 2.5 grams of hydrocortisone in 50 grams of finished product. Calculate the percent weight over weight strength, and round to the nearest tenth. So you can see here the cream contains 2.5 grams of the drug or solute in 50 grams of the final product, which is obviously the preparation. So you would divide the 2.5 grams or the 50 grams in this case, and then multiply it by 100, and that will give you the amount here. So 5.0% would be your answer, weight over weight. The next one here is another percent strength calculation. You guys can use it as a practice problem. You can see a solution here, which is shown here is 39.97%. Notice that some of these do require some conversion, unit conversion to be able to solve this practice problem. So you can see how it kind of builds upon those basic concepts in these future pharmacy calculations problem. Specific gravity is equal to a weight of substance over weight of equal volume of water. And so it's very important to understand this concept as well. You may see questions on that. And you can see here what is the weight grams of 18 fluid grams and 4 minims of a solution having a specific gravity of 1.08, and you would round to nearest tenth. And you would do your conversions. You would convert them all in milliliters, and then you would find out what the weight is. And so this is another calculation you may see regarding alcohol calculation, where it involves measures and proof. And so these are some other concepts to understand. Here's a practice question for you all on that. I'll leave it up so you guys can take a look at all of this in terms of proof and you know, how much is required. So you can see here 80 proof of vodka is equal to 40% alcohol. So that's usually what's going on here. It's usually you would just take that proof and divide it by 2, and that'd be your percent of that alcohol there. And so you can see how it's being done here in the problem here, where you could see there's 2 measures of 80 proof vodka. So you do the 2 times 1.5, because as it states, 1 measure is equal to 1.5 fluid ounces. And then you would take that answer and then multiply it by 0.4. So you would take the percent value and then move over 2 decimal places to the left, and then you would get a value of 1.20 fluid ounces. Same thing what you would do with the liquor, and then you would do whiskey very similarly, and then finally you'll get the total ethanol value. You would convert it to milliliters, and then you would use the specific gravity in this case and multiply it by the total amount in milliliters, and then you would get 42.75 grams of alcohol, ethanol. In this situation, you would round it, so it would be 42.7 grams ethanol in this case. Then the next problems involve dilution. Dilution, sometimes when you're doing a mix, you're mixing a solution, you have the drug in there, which is obviously needs to be concentrated with some sort of water, and you would get the volume you need for the starting product. Um, then you have to figure out what the desired concentration, desired volume should be on that solution. So you'll have situations where you have to do some conversion, where you have 10% solution need to prepare 100 milliliters of 2% solution. So this is the equation C1V1 equals C2V2. Um, you'll basically plug in the values here, and you wouldn't really need to include the percent in the problem by itself. You could just put 10 V1 equals to 2 times 100 milliliters, and then you would just do the um, math there, and you'll get the volume there as 20 milliliters. So that's how much starting product you would need to prepare the desired concentration, desired volume of that same product. So if you were starting out with this much drug or this much liquid in it, and to make this much concentration, how much would you need to make? Let's say you have 50 milliliters and you have to make 100 milliliters of it. How much volume would you need, or how much concentration would you need to make that much? So this is the kind of conversions you might encounter in your pharmacy practice on your pharmacy exams. Um, so be sure you're familiar with this concept here. Um, the next part is the dilution problem. A pharmacist needs to prepare 250 milliliters of a 4% solution using 20% stock solution. So, how many milliliters of 20% solution are needed? So, here's the solution. You would just need 50 milliliters in this case. Um, so, you'll just practice through these dilution problems, and it should be okay. This next one is how many quarts of purified water should be added to 3 quarts of a 60% solution to prepare a 15% solution. You would round it to the nearest whole quart here, and you can see the solution here. There's 3 quarts. You multiply by the 60%, which equals 180, and then you would divide it by 15, which is 12 quarts. And then you would subtract it, because to take into account it says added to, so you're trying to figure out the difference there. So you just divide this amount, or subtract this amount to this amount, and then you would get the 9 quarts. Alligation is is another technique. It's a shortcut used when you mix two different concentrations to make a desired concentration. So suppose you have these two solutions, 20% solution, a 5% solution. You want to make a 10% solution. So you would basically do a diagram like this. You list the H, which is a higher concentration right here on the left. And then the L, which is a lower concentration, 5% solution. And then in the middle, which is M, I labeled it M, which is a 10% here solution. You will subtract the 10% by the 5% to form 5 parts. And then 20 minus 10 here, 20% minus 10% to form 10 parts. And so once you obtain the parts, you can represent it as 5 parts of 20% and 10 parts of 5%. So you need 1 part of 20% for every 2 parts of 5%. So that's how you would basically figure out how to solve an alligation type of problem, which involves mixing of two different concentrations. Um, so let's take a look here. Here's a practice question on that. Um, and then you can see how it was performed here as well. Um, Not exactly the same way as the one I showed you earlier, um, but it's similar. Um, so be sure you understand that concept there on alligation. Um, the next thing is on ratio strains. Sometimes prescriptions might show 1 colon X, which is essentially how ratio strength will be written. This essentially means 1 gram or 1 gram over 100 milliliters or 1,000 milliliters or 10,000 milliliters. So it's usually just like the weight over volume. So that's what that represents there. And then the percent strength in ppms. ppm stands for parts per million. Um, is represented as grams of solute over 100 milliliters. Um, and 1 ppm equals to 1 milligram per milliliter. So just a quick shortcut in case you were wondering how to remember that concept. Um, so here's a dilution problem. Um, Pharmacist adds 798 milliliters of diluent to 2 milliliters of a 110 acetic acid solution. What is the concentration of the final solution expressed as ppm? So I don't think you should be confused between that, since we just already talked about 1 ppm equals to 1 milligram per milliliter. So you could just represent it as milligrams per milliliter. So if you know how many milligrams per milliliter, you can probably figure out the ppm in this case. Um, so you would just perform calculation like this. You could see how the dilution equation uses the C1V1 um, technique, and um, you would just convert that percent to ppm. Um, you can do it this way. I think it would be a little bit easy to show it differently. Let's take a look and see if it works this other method or this other way. Um, so we could just make it like this, where you convert the um, percent value that you get C2, right? And you could just make it 0.025 grams over 100 milliliters, because that would be essentially how you would show the percent value based on weight over volume. And then what you want to do is you can just do unit conversion here, because like I said, it's milligrams per milliliter. So you're going to take the 1,000 milligrams, which is obviously 1 gram, and you'll just go ahead and multiply it. You can actually cross out 2 of these zeros, so you don't need to worry about that. And then you would just multiply by that, and you get um, 0.25. So this may be a little bit confusing. We should probably take a look at it a little bit differently here. especially since it's showing. Let's take a look here. And we're going to try to make this concept a little bit easier. I'm not sure if this question is really going to work that way, but at least we can try it. Obviously, when you add this with this, you're gonna make 800 milliliters, so we know that much of the final volume. And we have 1 of 10, which is there, and not sure where they're getting that 10% from, but let's see. I think they just did the 1 over 10 times 100, which makes sense since you're doing the that ratio there. So, and as I mentioned, ratio is grams per milliliter here in the previous section. So you would just multiply it by 100, and then you would just get the percent, which is the 10%. And then the 10% you would just multiply it by which equals to 20, and then 800 divided by 20, which equals to 40, which I don't know where they're getting the 0.025%, but we'll check it out here. So that is the concentration. So now if we take the 40 grams over 100 milliliters, which is essentially how concentration is written, multiplied by 1,000 grams per milliliter, we can assume possibility getting so essentially you can't take the fact that hold on just a second, I think I messed up here. It's the other way around. I didn't look at it that way. So you're trying to figure out C2 in this question, and what you have here is you have C1 and V1. So you're actually dividing the other way. So the 20 grams, or 20, just keep it at 20. And 20 over 800. And then you would just find like 2 over 80, which equals to 1 over 40, which equals to 0. Well, let's not do decimals here. So that's going to be your 1 over 40, which means it's going to represent your percent there. So that's going to be 1 over 40, which is 1 gram, 40 mLs in this case, multiplied by 1,000 milligrams per um, 1 gram. And then you would get here 100 over 4, which equals to 25. 25%. Okay, so that's your 25% in this case. Um, or in the other case, 25 grams. Sorry about my writing. I'm just verifying this so you guys can see it a little bit more clearly. Um, so it would be 25 times 10, which is 250 milligrams per ml. So that's how you would get that 250 milligrams per ml. So I know it's a lot of steps, but if you need to do it this other method, it will actually work. You'll have to just basically what I did is, first of all, you have to read the prompt. The pharmacist is adding a diluent to the solution. And so you're going to get 800 milliliters of the final product. And that is your volume. That's your V2. Then uh, you have your C1 and V1 already listed because that's like your starting. It says diluent 2, so that seems like your starting product after that. And your starting product, you would have to represent that 1 over 10 as a percent, that's 1 gram over 10, and then multiply by 100%. So you would get a percent value on that. Once you get that, you can actually start working on the C1, V1 to get your 20. And then you would divide that 20 by 800, you get 1 over 40, 1 gram over 40 ml, and then you would multiply by, you would do the conversion here, which is 1,000 milligrams over 1 gram. And that would lead you to that will show you that it is 100, basically 100 over 4, um, that would be 25, which is equivalent to 25% because you're going to do it as 25%. Um, this might be a little bit more complicated right here at the end, so let's see if I can fix it up for you all because I don't want to um, make it more complicated than it really is. So we get a 1 over 40 over there, which is obviously listed as 0.025%. we can see that. Um, but we want to make sure that we understand what they're showing here in terms of grams or milliliters. So let's see if we can make it work. So 1 over 40. Um, hold on 1 second. So we could just represent this as the 0.025%. And which would equal to just, I would say, I don't know where they're getting that 10,000 from. So that's what I'm trying to figure out here. Seems a little bit interesting to see how it's showing here. Um, okay. So this is 0.025% multiplied by 10,000. Where's the 10,000 coming from? We'll have to see. We'll have to come back to this problem, but if anybody has a way of figuring out why, where the 10,000 coming from, that'd be great if you guys want to share that here in this for this slide. Um, so let's just move on for now. I know this type of problem can be a little tricky, even for me personally. It can be a little bit tricky. I might have to look more into it, but um, it would be interesting to see where they're coming up with the 10,000 from. That's the part that can probably be a little bit confusing to some of you. So we'll take a look at that in the future presentations. Um, so let's move on here. The next one talks about stock solution. A stock dextrose solution B is prepared so that 10 milliliters of solution B is diluted to 1 liter, produces a 0.2 milligram per ml dextrose solution. How many milliliters of a 60% weight or volume dextrose solution are required to prepare 150 milliliters of stock solution B? That might be a lot of words, And some of you might have a little bit trouble understanding that. So let's go over the solution and see how they've worked it out. So you can see here that there's 0.2 milligrams per milliliters um, right there, and you multiply by 1,000 milliliters to produce uh, 200 milligrams, and then you would divide it by the 10 milliliters, which would give you the 20 milligrams per milliliter solution. And you can see how it's kind of following along through the problem here. Then you would multiply that by 150 milliliters, because that is usually like your final stock solution. That's what you would multiply by. And you can see the 1,000 milliliters coming because of the 1 liter there. So you would be able to see that. And so you would get 200 milligrams there. And then you would figure out what the strength is there. You would have 60 grams over 100 milliliters of dextrose solution. And then you would just do the proportion there. Your X value would equal 5 milliliters. So that's what you would do in this case. So the next one involves mixing of two drugs. I'm not going to go over all of these for you, but at least you can take a look and see how they are worked out. Here's another mixing solutions problem and how that's worked out for you. Percent strength dilution problem. This is interesting to look at as well. Another concept to understand is the body surface area and pediatric dosing. I listed the formulas here for you for your reference. You can see how there's a square root here. I don't know if like the board exams will have those buttons on the calculator, but they'll probably have it simple enough for you to be able to calculate these types of problems. Um, but for your reference, for your pharmacy calculation scores, it is a good idea to see how these formulas are used. So I listed a calculation question here related to pediatric dosing. I'm not going to go through this. You can go ahead and practice them on your own. The solution is there. It's all clear, it makes sense, but it is there for your reference as well. Here's the ideal body weight and adjusted body weight equation. It is very important to understand this, especially when you're dealing with dosing or when you're doing vancomycin dosing or any kinds of dosing related calculation questions that involves body weight. And sometimes you have to see whether it is appropriate to use ideal body weight, adjusted body weight, or the um, the the body weight itself. So that's this is here listed for you for your reference. You can take a look at these problems here and its solutions. They're very simple ones. Creatinine, Cockcroft-Gault equation, another one commonly used, separated between females and males. There's the only separation is really that 0.85, which is multiplied by the creatinine clearance that's calculated here. And then here's a practice question on that. Then you have aliquot. Aliquot method is the amount of drug you need to when it's too small to measure accurately with available balance or measuring device. So before you start using the aliquot method, you have to calculate the minimum weighable quantity using this formula. And the formula is really just the sensitivity requirement times 100 divided by percent allowable weight. So you would do a question or problem like this, and figure out what the minimum weighable quantity is. And I listed out the steps here, how that's solved. And you would then you would actually, perform these series of calculations to get to how much diluent you would need, how much of the measurable drug you would need, and all of that. So this is for you. You can read through it and try to solve the question. This next one is on the um, milliliter version of it, so you can take a look at how it works with the graduated cylinder. The percent error problem, you may see one or two questions on that, or some more questions on this. So this one you're just calculating the percent error. That's basically all it is. So I'm gonna leave this up to you to try to solve that. Isotonicity is basically has to do with the osmotic pressure as blood and tears. So one of the most important methods of pharmacy calculation is understanding E value. The E value tells you how many grams of sodium chloride have osmotic effect as 1 gram of a particular drug. So that's something you will need to know, or they will actually provide it to you on the exam. They're probably going to give you an E value. The E value is where you have 1 gram of drug A equals to this much sodium chloride in grams. So as you can see here, 0.9% sodium chloride is typically used in this case. So basically, just understand that. And then freezing point depressions may use this formula. I have not seen that many of the sodium or the freezing point depression problems, but at least understand the isotonicity section on this. You'll see a couple of questions on that. So these are some of the formulas that's used to calculate the sodium chloride required, the sodium chloride equivalent, and the sodium chloride to add. So take a look at all of this and make sure you understand how to solve these types of problems. Then there's a buffer equation, which involves a pH and pKa. Which buffers a solution that resists to changes in pH when small amounts of acids or bases are added. So Henderson-Hasselbalch equation is used in buffer ratio calculations to find out how much weak acid or conjugate base are needed to produce a desired pH. So that's essentially what this is. So it's usually base over acid. And then in some cases, they may just give you Ka instead of pKa. So you would have to figure out a pKa by doing the negative log of Ka. And then you can also calculate buffer ratio using this formula, which is 10 and then exponential pH minus pKa. So here's some questions. You guys can take a look at that. Reconstitutions, yes, this is a reconstitution practice problem you can use. And here's a capsule displacement calculation. Some of you may get confused on this one. I posted it here on just one question on it, just so you guys, one or two on it, so you guys can use that as practice. So a prescription calls for 30 capsules, each containing, you see drug A 20 milligrams, drug B 15 milligrams, and drug C 40 milligrams. So when the size one capsules are completely filled, then one capsule should hold um, 300 milligrams for 50 to 40. So that's how much a one capsule should be able to complete hold. Um, and then you gotta figure out how many milligrams of lactose are needed to prepare the 30 capsules. So before you get there, make sure you know the steps getting to that process. You have to basically divide it up between the three types of drug A, drug B, drug C. And then you're gonna have to use the lactose amount, which obviously they've given you um, here. And you have 280 as like the total amount inside that capsule. And you would just subtract it by the total amount that's calculated by each of those small quantities of that's used to fill each capsule. And you would basically um, multiply it by 30 so you can get the total amount of lactose needed. Then the next one is here is the milliequivalent review, which um, represents the chemical combining capacity of an ion. It takes into account molecular atomic weight and valence charge. So whenever you see something like milligrams, which has a 2 plus ion, that means the valence is going to be 2. So that's something you would have to know, especially if you've taken chemistry classes and they teach you how the periodic table works, and then on there they will show you the charges and the valences. So that's essentially how you use the or figure out the valence by charge. Um, Here's a table to give you the most common ones used in pharmacy calculations. And then I have a practice problem listed here for you all. Osmolarity is the number of osmoles of solute per liter of solution. And you can see it represents milliosmoles per liter. And the calculation, the formula is listed here, equals to gram over liters over molecular weight times the number of particle dissociation values and multiplied by 1000. This is a example problem here that you can work with. Then the Harris-Benedict equation is used to estimate the patient's basal energy expenditure, and it's expressed as kilocalories per day. So you can see here there's differences between male and female. Um, this is something I did not have to memorize. So most likely you guys won't have to memorize it in your uh, pharmacy program, in your exams. It's just going to be too many values you'll have to memorize. So this is one of those formulas that's probably going to be given to you on a test. Um, you'll have to probably know that you have to multiply the activity factor and the stress factor to calculate the energy requirement. And so there's a question here that uses that formula. And then here's some more body mass index, how that's calculated, and the units used for body mass index, and the categorization of what's considered obese, CT, overweight, healthy weight, underweight. And here's a problem on body mass index. TPN calculation information. Some of these you're going to have to memorize, like the lipid in your emulsion, the amino acids, dextrose, fat, protein, carbohydrate, all those values you should know when you're studying for the test. And then uh, this is a practice problem using those concepts. And that's pretty much it. So this will be the end of this first review. I'll have to repost or show you an updated post on the two questions we weren't able to completely figure out today, but I'll get back to you on those. So I hope you found most of the information very helpful to you, and feel free to let me know if you have any other questions, um, and we will look over it and let you know. Thank you for watching. You know, all have a good day. One other thing, for those of you who have been watching this video, um, to this video's reward code is going to be, or code word is going to be cardiomyopathy. So remember that. And when we have our next challenges, there will be a blank or a column where it will ask you what the code word is. So don't forget that. Anyways, thank you for watching. I hope you all have a good day.